Welcome back, AP Chemistry students, to Unit 5, Kinetics. Today we will be talking about Unit 5.3, the integrated rate law. So in our last video, we talked about differential rate law, which is when you were given concentration versus rate data in order to determine the rate law and the order of the reaction with respect to different reactants. And remember, all rate laws are expressed the same way, that the rate equals some constant times the concentration of your reactants raised to their order. In differential rate law, we had multiple reactants. So our rate laws could have looked something like this. Today we're going to talk about analyzing a different type of data in which you only have one reactant. This means that only one reactant plays a part in your rate law. In order to do this, we look at concentration versus time data, known as the integrated rate law, and we analyze that data and manipulate it to try to figure out which circumstances provide us a graph with the straightest line. A straight line would have an R value nearest 1. All right, so we will be looking at the statistical test, the R value for a linear regression. Integrated rate law only includes one reactant because we generally cause all other reactants to have such a high concentration that only one of them is involved in the rate determining step in a process known as swamping. And that is the process we will use in our lab for this unit. In the end, we will be looking at various graphs and determining which one provides the straightest line, and the slope of that line is our rate constant. Keep in mind, rate constants are always positive, so it's the absolute value of that slope, regardless of what the line looks like. So, quick overview, we will graph time versus concentration, just the data as it's given to us. And if that provides us a straight line, that's a zero order reaction, because as the reaction occurs, the concentration didn't really affect it in any way. The reaction just occurred, and therefore it was consistent with time. In a first order reaction, the natural log of concentration versus time gives us the most straight line. In a second order reaction, it's the reciprocal of concentration. And if you remember them that way, that it's concentration, natural log, and reciprocal, that's alphabetical, right? Concentration, natural log, reciprocal, and that's how I personally remember it, that if I put them alphabetically, they line up with our numerical values. When it comes to the integrated rate law, we will only do this with reactions that are 0, first, or second order. We will not have any fractional orders, and we will not go past second order reactions. So, if concentration versus time gives us an R value that's closest to 1, that means we have a zero order reaction. Everything kind of falls into line as long as you remember your linear regression formula, y equals mx plus b. Y is our concentration, and x is time. B stands for the y-intercept. So the concentration at time 0. So our initial concentration is our y-intercept, and our slope is k, but the concentration versus time will always have a negative slope, so please remember that k is an absolute value. If the natural log of concentration versus time provides us the straightest line, if our R value is closest to 1 in that case, that means that our y values are the natural log of our concentration. So if we want to know the concentration at a particular time, you will have to undo that natural log, meaning you'll have to raise e to whatever y is in order to determine the concentration of your reactant at a given time. X remains time, so that's pretty straightforward. And again, the y-intercept is the natural log of the concentration you initially started with. So in order to find the initial concentration, again, to undo a natural log, we raise e to that value. Natural log of concentration versus time will also provide a negative slope. So again, the absolute value of our slope is the value of our rate constant. If the reciprocal of our concentration provides the straightest line, our R value closest to 1, our Y values are the reciprocal of our concentration. So in order to determine the concentration, simply take the reciprocal of our Y values. So if you need to know the concentration at a given time, simply take the reciprocal of the value of Y. Keep in mind that the y-intercept will also be the reciprocal of the initial concentration. This is the only time in which our slope will most likely be positive, so the slope is the rate constant. In years past, you used to have to graph your data. They would give you data, you'd have to graph it. However, since not all students have access to a graphing calculator on exam day, we will now provide you with graphs and either ask you, hey, here's all three, what's the order of the reaction with respect to this reactant, or we will provide you one graph and say, what is the order not? All right, meaning we'll give you a graph where it's definitely not a straight line. And that will become more clear as we do free responses in this little subunit. So let's get some practice. As I said, you will be provided graphs as well as the data. So here we have the decomposition of dinitrogen pentoxide, and we have concentration versus time data, meaning I know that I am going to do the integrated rate law, looking at our graphs to determine which one provides us the straightest line. So this first question says, determine the rate law and calculate the value of K. In our data, we have our different options. Concentration versus time is 0 order, natural log versus time is first order, and the reciprocal versus time is second order. In order to determine which one is correct, we look for the R value that's closest to 1. So obviously, the natural log is going to be the graph we'll use. The other two now are just extraneous information. We don't need them. So, to determine the rate law, it's just a matter of writing rate equals K times the concentration of the reactants raised to their order, which we said was first order. The value of K is simply the absolute value of the slope. So the value of K here is 0.0069. Our units of K are always time in the reciprocal, so time to the -1, so seconds to the -1, and then molarities to the negative overall order -1. Our overall order here is just 1, so 1 minus 1 is 0. So we have no molarities in our units. So our rate law is rate equals K, concentration times the concentration of dinitrogen pentoxide raised to the first. Our value of K is 0.0096 for each second. And all the other questions now are simply a matter of utilizing this formula. Our formula is that the natural log of our concentration has to equal a negative 0.0069 times time minus 2.3026. So if we keep that in mind, we can answer all these questions just doing simple algebra. Determine the concentration. So we now want to know, determine this value at 250 seconds. So 250 is the value of x, our unit of time, and we're going to determine the concentration. So taking our linear regression, that the natural log of the concentration equals this whole expression, simple calculations tells us that it's a negative 4.0276. Now, is that an answer? It is, but it's not the answer they want. We're looking for a concentration. What we have here is the natural log of a concentration. So to undo a natural log, you raise e to that value. So we're going to do e raised to the negative 4.0276. And that will give us the concentration of dinitrogen pentoxide, which is 0.0178. It's a concentration, so let's call it molarities. So at 250 seconds, we have a concentration of 0.0178. Does that make sense? If we look at our data, 250 seconds would be right here. And we came out with a value of 0.0178. Does that track? Yes. We would expect a value somewhere between 0.025 and 0.0125, which our value fits. So yes, our answer makes sense because it is between 0.025 and 0.0125. Second verse, same as the first. What is the concentration at 600 seconds? Again, the natural log of the concentration is going to equal a negative 0.0069 times 600 for our unit of time, minus 2.3, and plugging that expression into our calculator, we get that the natural log of our concentration equals a negative 6.4426. Again, that is the natural log of our concentration, not our actual concentration. In order to undo a natural log, we'll raise e to that value to find the concentration of dinitrogen pentoxide, which we come out to be 0.00159. Does our answer make sense? Well, at 600 seconds, we got 0.015. 600 seconds would be way down here. 0.0015 tracks. It should be substantially less than 0.006, which 0.0015 is. So yes, our answer is justified because it needs to be less than 0.006. Now, letter D is a little different. Letter D asks us to find the time at which the concentration is 0.0015. So we know it's going to be somewhere in the realm of 600 seconds because our previous answer. So we know we're looking for somewhere around 600 seconds. But to find the exact value, we can plug that concentration into our linear regression. So in this case, we are looking for time, but we have the concentration. So I can plug those values in. The natural log of 0.0015 has to equal a negative 0.0069 times time minus 2.3026. Some algebra means I need to get t by itself. So if I add 2 to both sides and then divide by 0.0, I can solve for time on its own. And then it's just a matter of plug and chug into your calculator. Don't forget your parentheses, because that's where you'll run into some trouble. So the natural log of 0.0015 plus 2.3026 is one expression, and then dividing by negative 0.0069 is the other, to give me 608.7 seconds, or 609 seconds, if you're going for 3 significant figures. So as long as you can do linear regressions, y equals mx plus b, and keep track of what y and x mean, you can do the integrated rate law. So one more example, let's do together as a group. On page 15 of your packet, you will find this practice. Why don't you pause the video and see if you can do A through C. From our data, we see that our first graph doesn't even give us an R value because it obviously curves. The second one has an R value that's pretty close to 1, but it's not as close as the third one here. And these are actually in order. Concentration is 0 order, natural log is first order, reciprocal is second order. This reaction is second order with respect to butadiene. So our rate law, the rate equals K times the concentration of butadiene raised to the second, because it's a second order reaction. The rate constant is the value of that slope. So 0.0142. The units of the rate constant are always the reciprocal of time. In this case, time is expressed in seconds. So seconds to the -1, and our molarities are the overall order 2 minus 1. So 2 minus 1 is a 1. So molarities to the -1. First order reactions, finding the half-life is fairly simple. Find when half the sample has decayed. In this second order reaction, it's equally as simple, it's just not as easy to see on the graph. We started with an initial concentration of 0.016. So we are going to need to find when the time when we end up with half that initial concentration. So half that initial concentration is 0.00835 molar. So the concentration of butadiene that we're looking for is 0.00835, which unfortunately is not in our table, but we can use the linear regression to determine that value by plugging in this concentration into our linear regression, but not that concentration directly, because remember, this concentration is our y, but it's the reciprocal of the concentration. So the first thing I'm going to do is take the reciprocal of the concentration I'm looking for. So my value for y I'm going to plug in here is 119. So with that, I can solve for x. 119 equals 0.014 times x plus 59. So subtract 59 on both sides, and then divide by the slope. Will give me the time I am looking for, which comes out to be a unit of time, which comes out to be 4,262 seconds. And there's the work in case my grader wants to know where I got that value from. Hopefully you were able to determine this answer on your own, in which case please finish all of practice E.2. It is a couple pages. There are multiple examples, and in each one I provide you the graph and the R value. So please finish page 15 and 16. Next class, we will do a lab by swamping, meaning we will take reactants and we will make one in such massive concentration that the rate determining step has to be the one that is not that concentration. All right, and we will determine the amount of product by spectrophotometry, meaning as we pass light through the sample, we'll use Beer's law to determine how much is actually in that sample. Please make sure you do your pre-labs, and I will see you next time when we wrap this whole thing up, finish by talking about catalysts and mechanisms, and I will see you then.